Analyzing systems with singular matrices. Now, to start, let's take a quick look back at what we have already covered. In our previous subsection, we explored how to solve a system of linear equations, specifically for the case where the coefficient matrix, let's call it A, is non-singular. In mathematical terms, this simply means that the determinant of A, which we write as absolute value of A, is not equal to 0. In these cases, we were able to find a unique solution for our variables because a non-singular matrix allows us to calculate its inverse, which we denote as a inverse. This inverse is the key tool that lets us isolate our variables and find that one specific answer. However, as we move into today's topic, we need to prepare for more complex scenarios. In many practical and theoretical applications, we encounter what we call a singular matrix. This is a special case where the determinant of A, or absolute value of A, is exactly equal to 0. As we will see in the next few slides, when this happens, the standard method of using an inverse fails, and we have to use a different diagnostic approach to understand what is happening with our system of equations. Welcome, everyone. Let's begin our new session on analyzing systems with singular matrices. Characteristics of singular matrices. Now that we've established what a singular matrix is from our previous slide, let's look closer at its specific characteristics. First, when the determinant of matrix A, which we write as absolute value of A, equals 0, the matrix A does not have an inverse. This is a crucial point because it changes how we approach the problem. Because there is no inverse, the standard formula we used previously, where x equals a inverse times b, simply cannot be applied here. We can't use that shortcut to find our variables. As a result, the system of equations does not have a unique solution. We aren't looking for just one single point where these planes intersect. Instead, we are faced with two possibilities. The system will either have infinitely many solutions, meaning the equations overlap in a line or a plane, or it will have no solution at all, meaning the equations are inconsistent and never meet. In the next slide, I will show you the specific mathematical tool we use to figure out which of these two cases we are actually dealing with. Understanding the role of the adjoint matrix. Now, you might be wondering, if we can't use the inverse to find a unique solution, how do we actually distinguish between having no solution and having infinitely many solutions? To find out, we are going to use a very specific property involving the adjoint of a matrix. Let's take a moment to recall the standard formula for the inverse of any square matrix. A, we know that an inverse equals 1 over the determinant of A, multiplied by the adjoint of A. As we discussed in the previous slide, when the determinant of A is equal to 0, we run into a mathematical roadblock because we simply cannot divide by 0. This means the standard method is off the table. So, instead of looking at the inverse, we shift our focus to something else. We need to examine the product of the adjoint of A and our constant matrix. B, we write this as the adjoint of A, all multiplied by B. Think of this specific product as a diagnostic tool. Just like a doctor uses a test to identify a condition, we will use this product to analyze the nature of our system and determine exactly which case we are dealing with. In the next slide, I will show you the specific criteria we use to interpret this result. The decision criteria. Suppose we are given a system of linear equations represented in matrix form as a times x equals b, where we have already determined that matrix A is a singular matrix, meaning the determinant of it equals 0. In this situation, we can't use the inverse method, so we must apply one of these two rules to find our answer. First, let's look at case 1, which is the no-solution case, also known as an inconsistent system. If we find that the determinant of A is 0, but when we multiply the adjoint of A by the constant matrix B, the resulting matrix is not equal to 0, then the system is inconsistent. In plain English, this means the equations are essentially contradicting each other, and there is no possible set of values for our variables that can satisfy all the equations at the same time. On the other hand, we have case 2, which represents infinitely many solutions, also known as a consistent system. This occurs if the determinant of A is 0, and when we perform that same calculation, multiplying the adjoint of A by the constant matrix B, the result is a zero matrix, where every element is 0. In this scenario, the system is consistent, meaning the equations are redundant or overlapping, and there are an infinite number of solutions that work for the system. Now that we understand that the adjoint matrix serves as our diagnostic tool, let's look at the specific decision criteria we use to analyze the system. Keep these two specific conditions in mind, because in the next slide, I will show you a clear, step-by-step procedure you can follow to perform this analysis every single time. Step-by-step procedure for analysis. Now that we understand the theory behind singular matrices and the role of the adjoint matrix, let's talk about how you can actually apply this in an exam or a problem-solving scenario. I want you to think of this as a systematic checklist. To analyze a system with a singular matrix, you simply follow these 5 manageable steps. Step 1. Your first task is to organize your data. Take your given system of linear equations and write them out in the matrix form. A times x equals b. This sets the foundation for everything else we are about to do. Step 2. Next, you need to calculate the determinant of your coefficient matrix. This is the most critical diagnostic step. If you find that the determinant of A, which we write as absolute value of A, is equal to 0, then you know you are dealing with a singular matrix. If this happens, don't stop there. Proceed directly to the next step. Step 3. Now, you'll need to find the adjoint of matrix A, which we denote as A. This is a bit more labor-intensive, as it involves finding the cofactors for every single element in the matrix, and then taking the transpose of that cofactor matrix. Be very careful with your signs here. Step 4. Once you have your adjoint matrix, your next move is to compute the matrix product of the adjoint of A and the constant matrix B. We represent this as A times B. Step 5. Finally, you simply observe the result of that product, A times B, to reach your conclusion. There are 2 possible outcomes. If the resulting matrix contains even a single non-zero element, you can conclude that the system is inconsistent and has no solution. However, if the resulting matrix is a zero matrix, meaning every single element in that matrix is 0, then you have found a consistent system with infinitely many solutions. In the next slide, we are going to walk through a concrete, numerical example to see this exact procedure in action. Illustrative example. Now that we have understood the theory and the decision criteria, let's put this into practice with an illustrative example. Imagine we are working on a real-world logistics problem. Suppose we are analyzing 3 different delivery routes to optimize for cost and time, and this analysis has resulted in the following system of linear equations. X plus y plus z equals 2, 2x plus 3y plus 2z equals 5, and 2x plus 3y plus 4z equals 11. To begin our analysis, following the procedure we just discussed, step 1 is to represent this system in matrix form. We define our coefficient matrix A with the first row being 1, 1, 1, the second row being 2, 3, 2, and the third row being 2, 3, 4. Our variable matrix X contains X, Y, and Z, and our constant matrix B is 2, 5, and 11. Next, we move to step 2, which is to calculate the determinant of matrix A, denoted as the absolute value of A expanding along the first row. We get 1 times the quantity 3 times 4 minus 2 times 3, minus 1 times the quantity 2 times 4 minus 2 times 2, plus 1 times the quantity 2 times 3 minus 3 times 2. When we simplify this, we get 1 times the quantity 12 minus 6, minus 1 times the quantity 8 minus 4, plus 1 times the quantity 6 minus 6. This simplifies further to 6 minus 4 plus 0, which equals 2. Now notice something important here. Since the determinant is 2, which is not 0, this specific system is non-singular. As we learned in our very first slide, this means a unique solution exists. However, to truly demonstrate the singular matrix case we've been studying today, we need a determinant of 0. So, let's modify our third equation to be 2x plus 3y plus 2z equals 11. Let's look at this revised example for the singular case. Our new system is x plus y plus z equals 2, 2x plus 3y plus 2z equals 5, and 2x plus 3y plus 2z equals 11. If we rewrite this new matrix A, the first row remains 1, 1, 1, the second row is 2, 3, 2, and the third row is now also 2, 3, 2. When we calculate the determinant of this new matrix A, we get 1 times the quantity 6 minus 1 times the quantity 4 minus 4, plus 1 times the quantity 6 minus 6. This results in 0 minus 0 plus 0, which equals 0. Because the determinant is exactly 0, we have officially encountered a singular matrix. This means we cannot use the inverse method, and we must proceed to the next step, which we will see on the next slide, to determine if this system has no solution or infinitely many solutions. Finding adjoint and analyzing. Step 3. Finding the adjoint of matrix A. We begin by calculating the cofactors for each element in our matrix. For the first row, the cofactors C11, C12, and C13 all result in 0. For the second row, we find that C21 is 1, C22 is 0, and C23 is negative 1. For the third row, C31 is negative 1, C32 is 0, and C33 is 1. By taking the transpose of this cofactor matrix, essentially flipping the rows and columns, we arrive at the adjoint of A, which is the matrix you see displayed here. Step 4. We must now compute the product of the adjoint of A and matrix B. We multiply our adjoint matrix by the constant matrix B, which consists of the values 2, 5, and 11. Let's calculate this row by row. For the first row, 0 times 2 plus 1 times 5 plus negative 1 times 11 equals negative 6. For the second row, 0 times 2 plus 0 times 5 plus 0 times 11 equals 0. And for the third row, 0 times 2 plus negative 1 times 5 plus 1 times 11 equals 6. This gives us our resulting product matrix, negative 6, 0, and 6. Step 5. Finally, we reach our conclusion. We look back at the decision criteria we learned earlier. Since the determinant of A is 0, but the product of the adjoint of A and matrix B is not a 0 matrix, because it contains non-zero elements like negative 6 and 6, we can officially conclude that the system is inconsistent and has no solution. Now that we have established in the previous step that the determinant is 0, we proceed to the final calculations to determine the nature of our system. This brings us to our final summary, where we will review the key takeaways and common mistakes to watch out for. Key takeaways. All right, let's take a moment to recap everything we have covered in this lesson, so that you have a clear summary to study from. First, remember the fundamental definition. A matrix A is called singular if its determinant, which we write as the absolute value of A, is equal to 0. Because the determinant is 0, we face a major hurdle. Singular matrices do not have an inverse. This means the standard method we used previously, where we solve for x by multiplying the inverse of A by B, simply becomes impossible to perform. So, how do we move forward? As we saw in our step-by-step analysis, the product of the adjoint of A and the constant matrix B acts as our diagnostic tool. This product is the deciding factor that tells us exactly what is happening with our system. To wrap it up, keep these two specific rules in mind. If the product of the adjoint of A and B results in any non-zero value, then the system is inconsistent, meaning there is no solution. However, if that same product results in a 0 matrix, where every single element is 0, then the system is consistent and possesses infinitely many solutions. Now, before we finish, I want to highlight a few common pitfalls to avoid during your exams, which we will look at on the final slide. Common mistakes. Now, as we wrap up our lesson, I want to pause and highlight some common pitfalls that students often encounter when working with singular matrices. Being aware of these will help you avoid losing marks in your exams. First, a very frequent mistake is assuming that whenever the determinant of matrix A equals 0, the system automatically has no solution. Remember what we discussed in the decision criteria. a singular matrix can lead to two different outcomes. It could be an inconsistent system with no solution, or it could be a consistent system with infinitely many solutions. To be certain, you must never stop at the determinant. You must always proceed to check the product of the adjoint of A and the constant matrix B. Second, once you have calculated the determinant and found that it is 0, please stop trying to find the inverse of matrix A as we learned earlier. The formula for the inverse involves dividing by the determinant, and since division by 0 is undefined, the inverse simply does not exist. Don't waste your time attempting a calculation that is mathematically impossible. Third, pay close attention to your work when calculating the adjoint. A very common error is calculating the matrix of cofactors correctly, but then forgetting to take the transpose. Remember, the adjoint is specifically the transpose of the cofactor matrix. If you skip that final step of flipping the rows and columns, your entire analysis of the system will be incorrect. Finally, be very careful when interpreting your results for the product of the adjoint of A and matrix B. If you're testing for the case of infinitely many solutions, you cannot simply have 1 or 2 zeros in your resulting matrix. For the system to be consistent with infinite solutions, every single element in that resulting matrix must be exactly 0. If even one element is non-zero, then you are dealing with an inconsistent system, and there is no solution. Keep these points in mind, and you will be well on your way to mastering the analysis of linear systems.